You know, we use electricity every single second of our lives, but have you ever stopped to think about just how weird it is? It's full of these amazing paradoxes, and today we're going to crack one of its biggest mysteries wide open.
All right, so let's jump right in with the puzzle, one that gets right to the heart of what electricity is. Think about it. You flip a switch, and boom, the light's on. Instant. But what if I told you that the actual little bits carrying the power, the electrons, are moving like slower than a snail? Seriously, how on earth does that work?
Yeah, check this out. The actual average speed of one of those electrons drifting through a copper wire to light up a bulb is just about 1 millimeter a second. A millimeter. You could literally crawl faster than that. It's just unbelievably slow.
And this is the crazy part, the signal, the go command that tells all those electrons to start moving, that zips along at pretty much the speed of light. So you've got this snail's pace for the actual particle, but a light speed command. It doesn't seem to make any sense, right?
Okay, to get our heads around this, we got to take a step back and look at the big picture. We need to understand the fundamental rules of the road for electricity, and it really all boils down to three key ideas.
First, you've got voltage. The best way to think about this is to imagine electricity is like water flowing in a river. Voltage, that's kind of like the slope of the riverbed. It's the pressure, the push, that makes the water want to flow downhill. No slope, no flow.
Then there's current. This is the flow itself. So sticking with our river analogy, the current is how much water is actually flowing past you every single second. For electricity, it's just the amount of charge, the number of electrons moving through that wire.
And last but not least, we have resistance. You know, every river has got rocks and little narrow spots that get in the way and slow the water down. Well, in a wire, that's resistance. That's just anything in the material that pushes back and makes it harder for the current to flow.
Okay, so here's the really cool part. These three things, voltage, current, and resistance, they aren't just separate ideas. Nope, they're all locked together by this one elegant, super powerful little rule.
It's called Ohm's law. And yeah, it was figured out way back in 1828. It's like the golden rule for all electric circuits. And it's simple. V equals I times R. Voltage equals current times resistance. That's it. That's the basic math that runs our whole electrical river. And it's named after this guy, George Simon Ohm, a German physicist who, get this, figured out this incredibly fundamental relationship before anyone even knew what an electron was. Pretty amazing. All right, but here's where our nice, smooth river analogy kind of breaks down. It's helpful, but to really, truly solve our speed mystery, we have to go deeper. We need to zoom way in, right down to the microscopic level inside the wire. Because what's actually happening in there, it is not a smooth river at all. It's more like a completely chaotic sea of electrons. They're just zipping around randomly, thanks to heat, bouncing off the metal atoms like a million tiny balls in a pinball machine gone wild.
So what happens when you flip that switch and apply an electric field? Well, the crazy pinball game doesn't stop. The electrons keep bouncing around chaotically. But the electric field adds this tiny, almost unnoticeable nudge, a little push, on all of them in the same direction. And that super slow collective shuffle, that's what we call drift.
And that tiny, slow drift is the key. This is how we solve the whole puzzle. It all comes down to understanding the difference between the signal and the things that are getting the signal.
Okay, so here it is, the big reveal. When you flip a switch, you are not sending one specific electron on a journey all the way from the switch to the light bulb. That's not what happens. Instead, what you're doing is instantly creating an electric field through the entire circuit. That field is the signal, and that travels at the speed of light. It's like a command that shouts down the whole length of the wire, telling every single electron, the one by the switch, the one in the middle, the one right at the bulb, to start their slow drift, all at the exact same moment. They all start shuffling forward together. And that's it. That's why the light comes on instantly.
But wait a minute. What about all that chaos, all that bouncing around and colliding with atoms? You might think it's just a problem, something that creates resistance, but it's not. In fact, those collisions are the very source of the power we're trying to use.
See, every single time one of those slowly drifting electrons bumps into an atom, it transfers a tiny bit of its energy. And that extra energy makes the atom vibrate, just a little bit faster, a little more vigorously. Now take that one little vibration and multiply it by trillions and trillions of collisions happening every single second. All that shaking and vibrating is heat. It's exactly why the filament in a light bulb glows or why the wires in your toaster turn red hot.
And yep, you guessed it, there's a formula for that. The power that gets lost as heat is equal to the current squared times the resistance. All that fancy math is really just saying that the more stuff you have flowing, that's the current, or the more obstacles in the way, that's the resistance, the more collisions you're going to get. And more collisions means a whole lot more heat.
I mean, the source material just says it perfectly. The energy that the charges gain from the electric field gets shared with the atoms, and so the conductor heats up. That R for resistance in the equation, that's really just the large-scale result of all that microscopic bumping and grinding, which we cleverly turn into useful things, like heat for our toast or light to read by.
So if there's one thing to take away from all this, it's this really beautiful idea of two speeds. You've got the electric field, which is the command to move, and that travels at nearly the speed of light. And then you have the electron drift, this slow, powerful, coordinated march of trillions and trillions of particles all moving together to create the current.
When you think about it, the immense power of electricity isn't about some single heroic electron racing from point A to point B. It's all about the tiny, coordinated shuffle of trillions of them, all working in unison. And that kind of makes you wonder, doesn't it? What other small collective actions out there have that same kind of incredible power to change the world?